Go. Okay, so when you multiply radicals, you multiply the outside numbers, you can multiply the inside numbers, but you can't multiply outside and inside. And this looks like a FOIL problem, and that's what we're going to do. So we're going to do 8 square roots of 7 times 5 square roots of 7. And what you do is you do 8 times 5. And what is 8 times 5? So I'm going to write 40. And then the square root of 7 times the square root of 7 is the square root of 49, because 7 times 7 is 49, okay? Now, you guys, I know some of you will be like, well, that's a perfect square. Yes, it is. We'll get to it in a second, okay? Now we're going to do 8 square roots of 7 times negative 6 square roots of 3. We're going to do the same thing. We're going to do 8 times negative 6. 48 minus 48. And then we're going to do the square root of 7 times the square root of 3, which is the square root of 21. Then we're going to do 2 square roots of 3 times 5 square roots of 7. 2 times 5 is 10. The square root of 3 times the square root of 7 is the square root of 21. And then we're going to do the last one. Then we're going to do 2 square roots of 3 times negative 6 square roots of 3. 2 times negative 6 is negative 12. The square root of 3 times the square root of 3 is the square root of 9. Now what we're going to do is we're going to take care of terms and all of that. I noticed that when I multiplied, I got the square root of 49. Well, the square root of 49 is a perfect square. So this becomes 40 times 7. I noticed the same thing over here. I'm going to have 12 times 3, because the square root of 9 is 3. The middle, I notice that the radicand, that's the number underneath the radical sign, is the same. Just like terms, you guys, just like we can add 4x and 8x, you can only add radicals if the radicand, the number underneath the radical sign, is the same. So 40 times 7 is 280. Negative 48 plus 10 is negative 38 square roots of 21. Notice I just worried about the numbers in front. They're kind of like, they're the coefficients of the radicals. And then 12 times 3 is 36. And I just brought down the operation. Now I'm going to do 280 minus 36, which is 244 minus 38 square roots of 21. So I did the 280 minus the 36. That's how I got the 244. And I just bring down the 38 square roots of 21. If they're the same, you guys, that is basically going to happen. When you multiply radicals, it tends to mimic what happens when we multiplied imaginary numbers. The last two terms always kind of, the first term and the last term kind of combine, and those middle terms do. Again, remember, you can only add or subtract radicals that have the same number underneath. Okay, so that brings me to actually just physically adding and subtracting. In first period, you guys, they did ask, well, what happens if 21, there's a perfect square in 21? You'll have to simplify it. And so I want to show you what I mean by that in the next problem. So example 7 is 3 square roots of 45 minus 5 square roots of 80 plus 4 square roots of 20. Okay, there are 3 parts within this problem, okay? So we have to simplify 3 square roots of 45. We'll have to simplify this. We'll have to simplify this. Because you'll notice, well, we can't add them because all the radicals are different. Except that the first thing that you're going to have to do when anytime you get an adding or subtraction problem is you're going to have to simplify. So we're going to simplify 3 square roots of 45. So what are, and this 3, you guys, is just going to come down here. And we'll deal with it later, okay? It's just in the front. We don't have to do anything. It just comes, it's just going to come down. Let's simplify the square root of 45. So what are 2 numbers you can multiply to get 45? Okay. I'm going to circle 5 because 5 is prime. It means it only has 2 factors, one in itself. 9. What is 9? 3 times 3. And do I have a pair of something? What do I have a pair of? So I'm going to cross out those 3's because those are the ones I'm going to wear. I'm going to put this here. And then do I have anything left inside the radical? The square root of 5. So that means this answer is 9 square roots of 5. Now, I'm almost going to, you guys, most likely one of these or all of them are going to have a square root of 5 in them, okay? So I'm going to bring this 5 down. This 5 right here is just going to be part of my problem. And now I'm going to do a tree for 80. What are 2 numbers you can multiply to get 80?
16 and 5.
What?
16 and 5.
Oh. That sounded really good on the video, let me tell you that. What? Yes, 16 and 5. You could also use 8 and 10. You could also use 4 and 20. It's really up to you. Okay, I'm going to circle the 5. What are 2 numbers you can multiply to get 16?
4.
And then 2 times 2 and 2 times 2. So what do we have pairs of? 2's here, 2 here, and do we have anything left over? We have a 5, right? So that goes inside the... Since it's subtraction, I'm going to be a subtraction sign down. 5 times 2 is 10. 10 times 2 is 20 square roots of 5. Now we have one more. You guys, since this is a positive, a plus sign, I'm just going to bring down the plus sign. And now I'm going to bring down this 4 right here. And then I'm going to do 20. What are 2 numbers you can multiply to get 20?
5 and 4.
And then 2 times 2. And do we have a pair?
Yeah.
We have a pair of 2's, and then what's left under the square root is 5. So I have 8 square roots of 5. Now, we started off with a problem that we couldn't add or subtract any of them because they were all different radicands. You guys, a radicand is the number that's underneath the radical sign. Okay, so now we can add them. But when you do it, the square root of 5 is going to stay. You don't ever add or subtract radicands. You can multiply them, but you can't add them or subtract them. So what's 9 minus 20?
Negative 11.
Negative 11. What's negative 11 plus 8?
Negative 3.
So my answer is negative 3 square roots of 5. In first period, they did ask, well, what happens if you simplify them and like this was 8 square roots of 2? You would just combine these and you would leave the 8 square roots of 2. So they all have to be the same in order to combine all of them. If you have one that's different, and you guys don't be alarmed if you get one that's different and you're like, oh my God, I did something wrong. You might not have done something wrong. Sometimes they do leave just something that doesn't add or subtract, and you you would just leave it there. But you do have to simplify all your radicals. You can't just leave some of them and not do all of them. You have to simplify them. That is the big key. Are there any questions over example 7? Anything that you're not sure of or how I did it? Are we good before I take this off? So this is your final answer. So remember, adding or subtracting, the first thing that you need to do is simplify each radical. Okay, let's go to example 8. Okay, so radicals, just like imaginary numbers, we should not have in the denominator of a fraction. You should never have a 0 and an imaginary number or a radical in the denominator of a fraction. Although this doesn't look like it's in the denominator of a fraction, it is. Because what we're going to do is we're going to break it up. And we're going to write it as the square root of y to the 8th over the square root of x to the 7th. Now, in algebra, you learned how to do this, and probably when you did right triangles and you did special right triangles, you had to rationalize the denominator if there was a radical in the denominator. This is what we call rationalizing. In order to rationalize it, you're going to multiply the numerator and the denominator by the denominator. So what is in the denominator? The square root of x to the 7th. So we're going to multiply not only the top by the square root of x to the 7th, but also the denominator. Okay. You guys, anytime these are identical, your answer in the denominator, because they're identical, is just going to be what's underneath the radical. As long as they're identical, one thing can't be different. They have to be identical. And then what is the square root of y to the 8th times the square root of x to the 7th? It's the square root of y to the 8th, x to the 7th. Now, in first period, they were really hoping we were going to be done with this problem. But we are not done with this problem, okay? We still have y to the 8th and x to the 7th to contend with. So y to the 8th we can do. So what is 8 divided by 2? What is 8 divided by 2? 4. Then we can actually break down the y to the 7th into x to the 6th times the square root of x. What is 6 divided by 2? So I have x to the 3rd, and then I have a square root of x, and it's all over x to the 7th. We're still not done. Nope, we're still not done. I know, first period was like that too. They're like, this problem's got to end. It is. It's about to end. I swear to you. You guys, this is a perfect SAT problem because it has everything. It has a rationalizing denominator, it has simplifying, and then it has reducing. Okay, so we rationalized the denominator, we simplified, now we're going to reduce. There isn't anything to reduce the y to the 4th with, so we're going to leave y to the 4th. But look, we have x to the 3rd over x to the 7th. Well, we can subtract the exponents. What is 3 minus 7? -4. Since it's negative, the x's are going to stay in the denominator, and then we have the square root of x. That is our final answer. So the square root of y to the 8th over x to the 7th equals y to the fourth square roots of x over x to the fourth. That's a really fun problem, right? Yep, that's exactly what first period said as well. Okay. There any questions over that one?